everyone, thank you very much for sticking till the very end. I have the least interesting talk out of all the speakers, but I am very pleased that you stay with me all the way until the end. If it wasn't the booze that kept you here, at least, it was the interesting talks for sure. So if you want the slides, please go on to that link. Everyone, you already know that my name is Ramon. I'll tell you a little bit about me. I am from the Dominican Republic. I've been living all over the world for the last 13 years, 10 years in the US, 4 years in Australia, a little bit less than a year here in London. I've really enjoyed my time in each one of these places, first as a researcher, then as a data scientist, then as an educator, and now as a combination of all of the above. I'm very pleased to bring you this talk today. We at Seldon do a lot of machine learning serving and deployments of models, but my first real interaction with deploying models was actually in Chris's course. So I told him that I stole some of his content just to put it here in the slides and make my talk more interesting. So I hope I make you at least laugh with some of it. All right, so some of the things that I'm going to talk about today, I'm going to briefly touch over the machine learning lifecycle. By the way, I do speak quite fast, so if I am going too fast, just put your hand up and be like, Ramon, slow down. I'm going to talk about serving models, a general approach. Then I'm going to talk about how to serve foundation models. I'm going to give you one example in each one of these just to make it more concrete. I'm not going to go into super depth of it, but if you've never heard of these topics before, if you've never done it yourself, maybe you come out with something at the end of this talk. And then we can do a little bit of Q&A if we haven't been kicked out by then. All right, so the first one, the machine learning lifecycle. So you've probably seen this spectrum where you see MLOps in the middle, DevOps on one side, machine learning on another, data engineering on another. So what exactly are we talking about when we say the machine learning lifecycle? Well, on one hand, we have the problem definition. There's something that we're going to try and solve. There's something that we are trying to do. There's a problem. Then we're going to do some data engineering. Then we're going to do some feature engineering because, of course, we got to engineer some features. Well, even if we're doing foundation models and we are extracting information or putting information inside a vector database, we're still going to have to engineer features from a non-structured piece of data. We're going to create an embedding for, say, a piece of text, or we're going to create an embedding for an image or something of that sort. Then we're going to do the model training. Then we're going to do some model evaluation, model deployment, monitoring, and then data gathering, again, with the information that comes back from when we do predictions. At Seldon, we operate in this spectrum over here. But let's put it more into context, this thing here. So if we were to rank all of this into a hierarchy, where do things land? Or what kind of problems are we trying to solve? Well, some of the issues that we have at each one of these steps in the hierarchy is sometimes we have badly defined projects that lead to bad outcomes. Sometimes data gathering can require a lot of time, or they can be continuously changing. Sometimes in data engineering, we have very complex pipelines. I think if you go and look at one of the talks on high performance computing by the chief of AI at Ford, you will notice that they have a pipeline of models of about 1,000 models connected with one another to create simulations that allow them to test the shape and the aerodynamics of a car. That sounds like a lot of complex stuff. Then you also have feature complexity in the feature engineering space, which is what I just touched on. And then at the top in the hierarchy, you have model training. But that is where the money comes from, or where the money is at, in that little space over there. And then if you think about back again into the model space, then some of the things that you're probably going to ask yourself as you're thinking about the last end, because this talk is about serving, can I trust this model? Does it work as intended? Can I extend its usage? Is it compliant with current regulations? And then when you get to the model deployment, can I scale it up and down, left and right? Can I combine it with different pre and post-processing steps? Can I use its input as the output for another model? And then lastly, when you're monitoring everything that is coming back, when your model is making predictions, is my model healthy or drifting away? Has the user behavior changed? If it is not behaving as intended, why is this happening? So those are the things that I want you to keep in mind as we go through the serving process. When you hear about a particular way or a particular recipe of serving a model, think about those things. Is my model drifting away? Like, how can I, if I serve my model in this way, how am I going to capture feedback back? How am I going to use that to put it back into the model and make it a little bit better? All right, so then if you think about the spectrum of where all these things sit today, you're most likely having some sort of combination of cloud providers. There has been, interestingly enough, a move to local data centers, again, or buying your own infrastructure, especially because well, the GPU pool and there's you can save a lot of money if you know what are you going to spend in the next year and you have your own hardware. But needless to say, a lot of stuff is still, for AI, is still in the cloud. Then you have a layer of Kubernetes. Then you have a layer of data gathering, all of the steps that we talked about: data engineering, feature engineering, model training, evaluation, deployment, and monitoring. Then you have a client. You have a person using a laptop or a person using a phone. And then you have your users. They're going to talk via that client. They're going to filter that stuff back in, and then your pipeline is going to start again. So we operate in this space, and that's as much, and that is the most amount of plugin that I'm going to do for my company today. So then now that you have in your head the machine learning lifecycle, let's talk about serving strategies. So there's three kinds of methods before we talk about serving, and it's important to point them out. Batch, and then we're going to talk about all three of them. So when we talk about batch, think about big database sitting somewhere. That database, and then think about the machine learning engineer or the data scientist. They're going to build a model. Then they're going to create a funnel to pass that data through, combine it with your model, combine it with some compute in a cloud provider of some sort, and then with that, pass it back into a database, put those predictions in a database, and then pass it to the user sitting at home watching Netflix. And that's kind of the overview of batch predictions. You have a lot of data sitting somewhere. You predict, say, recommendations for a user, 10, 20, 50, 100 for the next day that person is going to log in, or maybe for the next week. And then you keep them in a database until you need to refresh them. So you don't need them in real time. Then we have online predictions. So online predictions, you have this person that comes in, fills out an application, say for a loan or a credit card, gets denied. Well, maybe not. That person is going to input fresh features from that day. Say that person has a new job, that person bought a house, bought a car. All those things affect credit score. So that person is going to have a fresh credit score, even if they applied for a loan in the year before. But if they did apply for a loan in the year before, that means that that model is going to take in historical features and fresh features at the same time. So we need a way to combine those two. And we cannot do it as a batch process because the user is going to come in with fresh data. That's what we call online inference. We have a model sitting somewhere in a server waiting for data to come in to provide a prediction back. And that's the cycle. So then we talk about streaming. If I had right now a model translating in real time what I am saying to you from I have a job, why did the chicken, and then comes back down and says, yo tengo un chiste, ¿por qué la gallina? That is streaming. I am talking and it's operating in real time. As I talk, I might change what I'm saying, and the model needs to adapt to what I'm doing. So that's streaming. Back to batch, online, and streaming. We got a sense of what those are. Can I get a yes? Okay, cool. So we got a sense of what these are. Now let's talk about model serving and deployment strategies. First, we have embedded models. So what are embedded models? We can put a model inside a website. We can put a model within a mobile app. We can put a model within an edge device. If we keep brainstorming ideas, we can probably find other places where we could stick a model at. Maybe in that clock over there, or maybe even in this screen doing something, I don't know. But we could do a lot of stuff with them. So let me give you an example with Python first. Here we are importing Gradio. We're importing the pipeline class from the transformers library. We're importing NumPy as MP because that's what the cool kids do in the streets. We have a transcriber. So we have the pipeline. We're picking up a model, whisper-based EN. Then we define a function that transcribes some audio. Have anybody here ever dealt with audio before? Okay, fantastic. So if I say something, because there's so few of you, if I say something incorrectly, it doesn't matter. Nobody else knows. So we have an SR, which stands for sample rate, and then we have a Y, which is the array of data that we have. The sample rate is going to be what divides that array of data. And if the sample rate is 32, so the human hearing, we can hear vibrations in the air from 10 hertz to 20,000 hertz. But any kind of sound or any kind of given piece of audio is going to go usually up to 44,100 hertz. Don't ask me why, I forgot the details on that one. But that Y is going to be divided by SR, and that's going to give you the length of the speech that we're hearing. So then we're going to get we're going to do some stuff with it. We're going to divide it by Y, and then we're going to get the sampling rate. We're going to get the actual value that we're trying to transcribe, and we are going to return the piece of text. We have a pipeline. Then next, we're going to create a little application that is going to be sitting somewhere. So if I do here, let me see if I can. Why is it not letting me? Oh, there you go. Hello, Mom. Can you hear me? It's not letting me do it. No microphone found. Okay, so that's the reason why. It did not find my microphone, but I really wanted to do it. But anyways, the output would have come over here, but my, I guess because I am connected to this thing rather than my computer. So that's probably why. Okay. So then let's go for the next one, but that's what the UI would be. That's an embedded model inside a piece of a UI. Now we can also do it with JavaScript. So for example, here we have an HTML file, and we have the type of document that we are created. And here we're going to be using the ONNX runtime JavaScript example quick start. I took it from the docs. Then next, there's the body. Over there, I'm trying to say hello to my mom. She's probably watching right now. She's back in the Dominican Republic. Here we are picking up the library, the ONNX runtime-web. And then the next thing that we're going to do is that we're going to add our function that is going to do something with the model that is going to be loaded on the client side. What are the caveats of this? We were talking about the size of these models. If you put one of those models in the browser on the client, on the person, then some bad stuff is going to happen. Like it's just not going to work out very well. And also maybe the weights could be affected by that. Maybe somebody could steal them and so on. But either way, you can do that. And here's an example of how you would put a model using ONNX inside some HTML file that could be served to the user. Okay. So there is an example in this page. If you were to go to the demo one, you could see, this is by Facebook, you could see a couple of examples of real-time usage of, I have read and agree, of course I do agree. You could see a real-time usage of JavaScript to rank the images on this website. So I highly recommend you go to it. But anyhow, there's a lot of things that you can do by embedding a model in the client. So when do you want to use it? When you're prototyping, when you're in the prototyping stage, if your model won't be changing or need to be retrained often, if machine learning is not crucial to the functionality of your website, you can probably afford to put it on the client, on the mobile app, on the website. When you want to minimize external dependencies, you want to have everything in one single place, what they call the monolith. If your website or application is relatively small and simple, and if it is crucial that updates to your monolith happen in a synchronized way. All right, so what about within a mobile app? So let's talk about the advantages of doing that, because now we just talk about putting a model inside a website. So increased privacy might be an advantage, but then at the same time, you have limited model interactivity. If you have it on the mobile device, you don't have kind of like access to it because the person could be using it offline, but it's usable offline. So offline inference. Then limited computational resources. Nowadays, a phone today has much more computing capacity than a phone maybe even 3-4 years ago, and let alone 10 years ago. So right now, we could run fairly sized models today inside a phone. And as a matter of fact, companies do already. Low latency, the model is there in the phone. It doesn't need to send a request somewhere via the internet. Storage constraints, the phone is going to have a limited capacity, or the app might have a limit itself. Energy efficiency, maybe potentially. Model maintenance and updates are challenges because if you're a user, I know many people that take a year or two to update apps in their phones unless they stop working, and that happens. Compliance with regulatory requirements, that might be an advantage because the data and the model and everything is inside the user's phone. Training limitations, if you have to retrain the model inside the user's device, then there's going to be some sort of limit at some point, potentially, and then bandwidth savings. All right, so then what are the tools that exist to do something within a mobile app? You have PySift, you have TensorFlow Lite, you have PyTorch Mobile, Core ML for Apple products, Flower Framework, TensorFlow.js, Transformers.js. And let me just point out something. PySift and Flower Framework, these are frameworks to train models on device. So they send the model to your phone. It trains the model there. It sends the weights back to a server, and then it uses what they call a strategy. Sometimes it's averaging up the weights, sometimes it's doing something else with them. So then what about within edge devices? These are quite similar to the ones on mobile, but there are sort of differences in them. So you can have reduced costs if you have a model within IoT devices. You can have, but the disadvantage is that you're going to have heterogeneous hardware. So I have an iPhone 10. It came out, or the iPhone X. It came out in 2017. So right now I have apps already telling me that they don't support my phone. So it's kind of like pushing me, buy the new one, buy the new one. And I got to do it at some point. But my point on saying that, if I train a model and I'm trying to service people that bought a phone within the last 3 years, am I missing out on income from people that could very well take advantage of my application and my model, but have devices that are much older than the one I have? So that's something to keep in mind. Low latency at the edge, but then at the same time, you can have connectivity issues if it depends on being connected to different devices to be able to do something. Think about it, for example, smart home. Autonomous operations, that's an advantage, but then you have limited processing power. Some of these devices, they cannot take more than, I think it is like 1 megabyte in a model or something like that. There's some ridiculous requirements to be able to serve models on the edge. Then edge-to-edge communication, it might be, back to the example of smart houses. Some of those devices are going to be connected with one another. Environmental factors. If you have, this is one of the coolest examples that I've seen. In Australia, there is a company called Blue what? No, not Blue Water. It's Blue Scout, I think it is. And what they do is that they put in regional parts of Australia, in farms, they put these devices. These devices suck in air and the spores in the air at different intervals throughout the day. What they do is that it gets pasted into a kind of like a piece of glass, and then a picture gets taken on it. Then a deep learning model analyzes the image, and it sees whether it detects airborne diseases. And the idea with this is that if you do this constantly and there's no airborne diseases, then you can help farmers reduce the amount of pesticides that they spray on their crops. And that way we get better food, and they also save money. So they started in Australia. They right now are in New Zealand, Australia, I think Canada, and they're trying to expand into the US because that's the big money-making machine. But yeah, so but if, going back to the environmental factors, if a big tornado comes over to one of those farms, it could very well blow this very expensive piece of equipment that has a model, the weights are lost, and so and so. So that's a downside. Distributed processing, resource constraints, all of them are going to be reduced network dependency. They can run offline. Scalability concerns. and so on. So some of the things that you can use, TensorFlow.js, again, ONNX runtime has a runtime for not Arduino, but Raspberry Pi. That is really cool. I highly recommend you check it out. And then OpenVINO is for devices made by Intel. Also quite cool. All right. So then back to this. So model as a service. This can be within dedicated hardware. So you rent an instance for AWS that has either a GPU or maybe doesn't have a GPU, and you have it sitting there, and it's always going to be there. So that's kind of like your baseline. You can have serverless. If you have never heard of serverless, I'm sure a lot of you have. But if you have never heard of serverless, you are charged for what you use. So this thing spins up and runs your model for as long as you need it. It charges you maybe by the second or by the minute. It depends. Some companies have different pricing models, but it scales down to 0 if nobody's using it. What's the downside of having a model served as a serverless function? If the model is quite large and you are going to serve it, it's been in cold for quite a while, then there's going to be something that they call the cold start problem. The model has to spin up again. The weights have to be downloaded from somewhere, and then you start producing value. You start producing predictions for your users. You can also have models as pipelines. I mentioned that 4 has about one pipeline of about 1,000 models in it. So what's an example? What's the recipe? There's a recipe for majority of these models that are served within its own device. And that recipe goes as follows. You have some sort of class somewhere, but technically you don't have to. You need 2 functions. You need a load function that is going to load the weights or the parameters of that model. And then you're going to have a predict function. That predict function is going to have some sort of input coming in, and then is going to use the model that you're going to load here, and then it's going to use it to make a prediction. So that's the general recipe. Then you have some sort of package that is going to say, package start my model. So focus on the load, then the predict. Then say, for example, now that we started the server, we're going to send in a request. This is how an HTTP request, this is how services are going to communicate with your model sitting somewhere, say, in the cloud. Then you're going to do some package, send my model to the cloud. And now you created your model locally, you started the server, you tested that it works, you send it to the cloud. That's kind of the general recipe. Let me give you a tangible example now. So here we have one of the tools that we create here at Seldon is ML Service, an open source tool. We are importing a class called ML Model. And the reason we're importing this class is because whatever model we provide it with is going to be served asynchronously. So we have here an async before we define the function. We are importing the weights for MusicGen, a very famous model by Facebook. It is originally called AudioCraft, but then at Hugging Face, they called it MusicGen. So you're importing the model and the preprocessor. You are sending in a piece of text that is going to be a list of text, and you are returning a NumPy array. Remember that we talked about the sample rate and then the array of numbers. I'm going to generate some stuff based on those inputs, and then I'm going to, I have some parameters, and then I'm going to return a list of array. I know already the sample rate, which is why I didn't put it there. And then I'm going to have a model-settings that is going to tell my server, this is the name of my model, and then this is the name of the file, model-file, and this is the name of the class that you are going to serve. If you have used different API packages in Python, that is going to look very similar. And then I'm going to do ML server start that, and that's how I'm going to start my server. So what's going to happen then? My server is going to start. It's going to say my model was successfully imported. Then I'm going to have an endpoint. I'm going to import a couple of stuff, the request library. I'm going to have an endpoint. I'm going to have some sort of parameter, say, for example, the guidance scale, then an array. Then I'm going to send that via a post request. I have my endpoint. I have some sort of input request. And then I'm going to run that code, and it's going to say Python test server.py. Now, the coolest part of this is that, yes, I'm going to get some data back, but I actually kind of want to give you an example of it. And then this is a pipeline that you could use, say, in Seldon Core, one of our flagship tools, where you could combine the inputs and the outputs of different models. But what I really want to show you is like how these models are actually doing in reality. Let me see if so that is a model similar to Music Gen. How crazy is that? The way that this just works. Let's see, Ariana Grande. This is all AI generated. And okay, so here's the point that I want to make. It's not just that, yeah, it's cool music and whatever, but it's also that this is the UI. And that model is not sitting behind the screen, behind the URL that I requested from somewhere in the cloud. That model is sitting somewhere in the cloud, and it is connected via the UI. The UI, when I click play or whatever, maybe they already loaded those songs here, to be honest. But if you go and hit try now, it doesn't know what you're going to input to create. So it's going to have to send that request to somewhere else. And that's kind of like the idea of how I want to drive this piece home, this last point home. So what are the advantages of this two? Improved testing and debugging, potentially, because you have a service that is decoupled from your user interface. So now you can focus on improving this thing while other people focus on improving the user experience. Increased complexity, because if you're a company or your use case depends on many, many models, then you're going to have to do a lot of testing to be able to improve them. But you also have flexibility on the stack. I could have one model with Python. I could have another one with JavaScript. I could have another one with Rust. I could have another one in whatever, Llama CPP. I could have 10 different models. So now I can pick my own stuff. Communication overhead, if you have too many things talking to too many things at once. Enhanced team collaboration, because now you can have different separation of concerns. Dependency management, you're going to have to, if you have different services and you get to pick your own tools, then you're also going to have to manage the dependencies of each one of those tools. Improve resource utilization. There's a lot of stuff, but we're running out of time. There's a few things that you can do to create models as a service. Hugging Face Spaces is quite good. Not only do they allow you to put the model inside a UI and host it for you, but they also give you an endpoint where you can use to query that model. So you can have the best of both worlds of these two examples that I've gone over. AWS Lambda, the coolest use case I've seen is somebody train a linear regression, take the numbers that they got and put it inside a Python function in a Lambda function and just run that. It is the most lightweight thing you can ever possibly imagine. And then they have another Lambda function also revising that the input was coming in the right way, but you're paying nothing for that. Bento-ML is a very cool tool for that. I just gave you an example with ML Server, RaySurf, Replicate Code is really good. Now, there's a very niche model or use case, which is called model as data. So this is where the model is inside a database. Now, I'm going to give you two examples, and one of them, I'm going to give you my take on this, and it's about Predibase. Predibase started with these models in the database, and for what I've seen when I went back to their website, now they just do LLMs. Don't know what happened there. Maybe it didn't. They didn't really have product market fit. I'm talking without knowing. I'm just saying. I'm going to give you an example of it. Then the other one is PostgreSML. This one is very, very new. They have a lot of cool examples in their website. So I highly recommend you see them because it kind of makes you wonder, what can you actually do with it? But just so that I can make this point concrete, here is the example of querying a model that lives in a database. Predict intent, predict defects, given select from images. So I don't know where the model is. I don't know how it's working, but I just know this is cool. But it's not there anymore. They don't have it on their website. So I found this in a hidden blog post, I don't know how many months back, because as you saw in Chris's talk, even a year is a lot in the current landscape of AI. So That's the last category. There's probably many other categories, but we only have so much time. With the foundation models, what are foundation models? You already had a lot of information about LLMs and foundation models, but I'll give you one definition. It's a large-scale neural network trained on a massive amount of data. Another definition is a models trained on broad data, often in a self-supervised way and at scale. Think about a transformer that can be adopted downstream for downstream tasks. Remember Jody's talk about generalized intelligence. But in reality, it is more data, put more data in and call it machine learning. It's more layers, and it is a lot of compute. Back to the first point that I mentioned. So how do they work? Self-supervised training nowadays. Then you have fine-tuning on a specific set of data. Think about a corpus of financial data. And then you have a task. Go ahead and tell me the predictions for next year on how this company is going to do, or tell me the sentiment of this article or whatnot. That's a task. So, but nowadays, really, it's transformers. I mentioned large neural networks, but transformers is the architecture that is really crushing it today. And then how do we serve them? Well, choosing a mid-range GPU in 2016 looked like that. Choosing a mid-range GPU in 2021 and beyond looks like that. You probably couldn't see any because it's a scarce resource. So what are the tools that we can use to serve these gigantic models? We can use Truss, RaySurf, Bento ML, One Diffusion, Seldon, Replicate Cog, Hugging Face Inference endpoints. They're quite very beefy endpoints that you can use, and I think it's a really cool solution. Potassium, which comes from banana.dev. I think they intended that as a joke, but it is a really cool tool. And if you want to learn more about it, so there's VLLM that Chris mentioned as well. This allows you to do continuous inference. So when you think about the LLM, if you have an LLM sitting somewhere and it's producing some output for 10 users at a time, if my question is, what is the capital of Spain, as Chris put earlier, but another question is, write me a poem. Those two, the response to those two is going to be completely different. But what's going to happen is that because we can only serve 10 people at a time, even though the first one finished already, we still have to wait till those 10 finish to go and serve the next 10. So continuous batching or continuous inference is going to be when one finish, even though I have a max amount of 10, can I go and start serving another one with that space that I have left? So VLLM allows you to do that. And then there's deep speed, which is if I have 10 GPUs, can I make them look like one? That's deep speed for inference and training. And then you also have NVIDIA Triton inference server, and they are about to come out or already release a continuous batching offering. So if you want to learn more about this, banana.com talks about, banana.dev, sorry. They have an amazing article on their website called How Inference Works, and they have a lot of cool pictures that really drive the point home better than I can. So, oops. Okay, so how do we serve them? So I have 2 slides here on an example. So back to the recipe again. Let's scratch the recipe. Talk about YAML files. So if you already know where your model is coming from, or you're going to be using an open source LLM, for example, I have an example here with Truss. You're going to point out, actually, I have cool things that are going to guide our eyes. So we're going to point it to the model, where it's sitting at. Then we're going to say, I'm going to use this kind of server, VLLM, for continuous batching. Then I'm going to use an example prompt, say, what is the meaning of life? And then I'm going to say, I'm going to use Python version 3.9, and these are the resources that I want. I want this accelerator. I want 4 CPUs. I want 16 gigs of RAM, and then I want to use a GPU as well. And then I'm going to say truss image run tag my truss, and then it's going to start my server. Because if you notice up here, then at the bottom we have truss image build. In this directory is my config file. Assign the tag of my truss, and then truss image run. Now my model is going to start on port 8080, but you can specify that if you want. And then I'm going to send, you there, Mom? And she says hello back. So Docker push my model is going to be somewhere. One key thing that I want to mention in this step is that when you're going to create a container from an image, you want to be able to specify whether you want to preload the weights or you want to leave the weights outside. If you think about how large these models are, you don't want to create an image or a container. You don't want to create an image that is 50 gigs in size. So you might want, what you want to do is to leave those weights out and then load them when the container is being created. And then that's really it for me. Thank you very much, everyone.